So good morning. Hope y'all's morning is going well so far. That your first period class was excellent. Today we are going to be starting chapter 7 on sampling distributions. But first, I did some grading last night for the chapter 6 free response questions and self-assessment. There was an error that a lot of you guys had, or those of you who've done the assessment. I saw the same error many times of the submissions that have been graded. I've only had like a quarter of them turned in, but you know, I saw the same common error over and over again. In the first question of the free response questions, having to do with the fat quarters, the fabric. So I've created some similar problems that I'm going to show you guys how to do properly this morning, so you can have a better idea of the expectation for that question. And if you already got graded for it and you received the feedback that you may want to revise that, this should help with that as well, so that you may be able to get an even better grade than you already have for that assessment. So yeah, we're going to start with that. And then we'll get into chapter 7, specifically section 7.1. All right, so I do recommend maybe taking some notes on this. It will be available, obviously, in the recording to see it again, but there you go. So with that, I'm going to try and call everybody in, see if they get here. There we go. And share my screen. That helps too. Alrighty. So here we are in our example space here. So in the problem for the chapter 6 free response questions, it's asking about the fat quarters. You're given the probability distribution of X, which represents the number of defects in one of these pieces of fabric, and it ranges from 0 to 4 or more. I've created a similar type example that is not the same problem, and it's not using the same numbers, but it's the same concept. All right, so for this example, I'm letting the random variable X equal the grade point of a student in a college algebra class. Right, so the grade point corresponds to the letter grade. If you get an A, you have a 4, B is 3, C is 2, D is 1, F is 0. Right, and that's how your GPA is calculated, is each letter has a corresponding value. All right, so we're using these values as possible values for a random variable X. Right, if a student gets an A, B, or C, then they pass the course. This is typical for college courses. You need to get a C or better to receive credit for that course. D's and F's do not get you credit. And as a side note, if you're trying to move past your first 4 years of college into a master's or doctorate program, you typically need to get a B or better in all of your major coursework. So there's that. But that's neither here nor there. So we're going to introduce a secondary random variable, Y, that represents the grade point of a student who passes the course, a student who's considered passing, which is students with an A, B, or C grade. Those are the ones getting credit for the course. They do not have to take it again. They pass. All right, so this here will be the represent Y, and we'll have the probability here for the table. Now the major mistake that students made on this similar type problem on the assessment was that they simply transferred the probabilities from one table to the other one. That's not correct, because if I just take the probability of Y being 2, 3, or 4, which are the possible values of Y, and if I just take these three values, 0.35, 0.30, and 0.18, that does not add up to 100%. It doesn't add up to 1, which is not a valid probability distribution for a discrete random variable. And the probabilities of these three options of y, those three options are the only options for y, have to add up to 100%. 0.35, 0.30, and 0.18 only add up to 0.83. That is not 100%. That makes that probability distribution invalid. It is inaccurate. All right, so we have to determine the actual probability of each of these possible outcomes for y. And we use what we know from x, but we have to do some math. All right. So if you made that error, if you're one of the people who have already submitted your free response questions and you made that error of just simply taking the probabilities from one table to the next, that made the rest of your work incorrect for finding the mean and standard deviation. And that's not because you used the wrong method to find the mean and standard deviation, it's because you had the wrong values. Right? It's an error that propagates itself throughout the rest of your work. So what we have to do to answer A here, right? Constructing the probability distribution for y is we have to use a conditional probability. Right? So we're reaching back into the previous chapter again on probability, and we have to determine probability of y equaling 2. Right, we'll do this one first. The probability of y equaling 2 is equal to probability of x equaling 2 given that x is also greater than or equal to 2. Right? Essentially, it's what's the probability that x equals 2 given that the student passed. Right? So if I know the student passed, what's the probability that they have a C in the course is what we're finding. Right? This is equal to the probability of x equaling 2 and x being greater than or equal to 2 divided by the probability of x being greater than or equal to 2. Right? So I have some stuff here. We know that the probability of x being greater than or equal to 2 is equal to those three probabilities added up, 0.35 plus 0.30 plus 0.18, and that equals 0.83. Okay, so that's going to be our denominator, right? So this is 0.83. The probability of x equaling 2 and x being greater than or equal to 2 is the same as x equaling 2. It's 0.35. Essentially, there's no other way for x to be equal to 2 besides that, so it's just that one number. So we get 0.35 over 0.83, and that gets us 0.42. So the probability of y equaling 2 is 0.42. And that's a rounded decimal. It's a longer decimal than that, but we rounded it to two decimal places because all of our probabilities in the first distribution are also just 2 decimal places. So I'm using the same amount of decimals, right? So essentially, what we get is the probability of x equaling the value we want divided by the probability of x being greater than or equal to 2, which then we can kind of use to do this a little quicker. So the probability of y equaling 3 is equal to the probability of x equaling 3 given that x is greater than or equal to 2, which will just be 0.3 over 0.83, and that gets us 0.36. Which at this point we could just say 1 minus 0.42 minus 0.36 and fill in the probability distribution for y equaling 4. We can also show the work, which is typically what's going to be asked. And this will be 0.18 divided by 0.83, and that will be approximately 0.22. And we also want to check that things worked out as they were supposed to. And we see that 0.42 plus 0.36 plus 0.22 equals 1. That means I have a valid probability distribution. Everything worked out as it was supposed to. Excellent. So this is the probability distribution for y. It's the probability that each of the 3 possible outcomes occur. Is there anything I can clarify with this part of the problem? And so essentially the same process needs to take place in the response question. Now, for the second part, determining the mean and standard deviation, there's not really a shortcut for this. This is just a regular discrete random variable. So we have to do the calculations. We got to push it through the calculator. All right. So for this one, we'll start with the mean. Right? When calculating the mean of y, right, that's equal to the expected value of y, which equals the outcome, the possible outcome of y. So we can say 2 times probability of getting a 2 plus 3 times the probability of getting a 3 plus 4 times the probability of getting a 4. That's the entirety of the calculation. I saw some students who were dividing this by like 3 or 4, right? Dividing by the number of outcomes there were. That is incorrect. The only time we find the mean by dividing by the number of outcomes is when we're simply adding up all the outcomes and dividing by that number of outcomes. So like a straight up, I collected a bunch of data, I'm adding them up, dividing by how much things I collected. This is not that scenario, right? This is a random variable. It works slightly differently. So we have to do this, and that's the entire process. We do the multiplication, add these things up, and we end up with 2.8. Right, so essentially, the expected grade for a student in this class is like a C+ or a B-, depending on how the scale is, right, of a student who passed the class. Then, so that's our mean. For the standard deviation, right, the standard deviation of y is equal to the square root of the variance. Right, we have to calculate the variance for this. Right, and we can do this all in one crazy big square root. And in this case, you'll have the outcome minus the mean squared times the probability of that outcome plus the second outcome minus the mean squared times the probability of that outcome plus 4 minus 2.8 squared times 0.22. You can do this all in one shot in the calculator if you want. You'll get the most accurate answer by doing it that way. If you're doing this in parts, and then adding it all up and then taking the square root, you might have some rounding error. So let's just keep that in mind. When we do this, we get approximately 0.77. Right, and this is our standard deviation. Right, so again, if you incorrectly found the probability distribution, you may have done the right method to find the mean and standard deviation, but you got the wrong result because you started with the incorrect values. Is there anything I can clarify here for you guys or explain in better detail? Okay. Then we'll move on to the next part of this, which was the other part that people got really confused on. So the second part of question 1 on the free response question was essentially in a different question. It had nothing to do with the results you got in part A and B of question 1. It kind of lived on its own within the same context because we were still talking about defects and fabric and things like that. So it was living in the same context, but a different question. So in this case, we have the mean and standard deviation for the number of defects on a computer chip made by Chipcore. Again, I've made these things up. And the mean and standard deviation is 1.2 and 0.36 respectively. Right, so that means that 1.2 is our mean, 0.36 is the standard deviation. Right, so we have those numbers. We're going to need those. The chips sell for $25 each, but are discounted minus, right, by $2.75 per defect. Right, so we're given a linear relationship between the selling price and the number of defects. Right, basically the same thing that's happening in the free response question. We're being asked to find the mean and standard deviation of the selling price, right, which is determined by this $25 price and whatever is discounted for the computer chips sold by Chipcore. Right, so first we want to define the things that we're going to be using. We don't just want to jump into the math. We could, but that could get muddy, right? So first, we're going to define two random variables. We're going to let C equal the number of defects on a chip sold by Chipcore. And we're going to let S, my S doesn't want to look like that. That looks like a Greek letter. And we're going to let S equal the selling price. Of a chip from Chipcore. Right, so these are our two random variables we're going to use. We know already that the mean of C equals 1.2 and the standard deviation of C equals 0.36. That's the given information that we got up here. Right, we're going to need those. And then S, the selling price, is equal to $25 minus $2.75 per defect, or C. So this is the linear relationship between S and C, the two random variables. All right. This is what we need to use to convert and transform the mean and standard deviation that we already have. Right. To find the mean of S, we use the entire linear transformation, right? Measures of center are affected by both adding, subtracting, and multiplying and dividing. Right? So it gets this whole thing. So the mean of S is equal to 25 minus 275 times the mean of C. Right? And that's going to be 25 minus 275 times 1.2. And that leads us to 2170. All right, so over the course of many chips, samples of chips, we would expect the price of a chip to be about 2170 on average. Right, based on the number of errors we expect, or number of defects. Right, then, right, so that's our mean. It gets the entire transformation. Standard deviation of S. Right? A standard deviation is a measure of spread. Measures of spread are only influenced by multiplying or dividing. They are not changed by adding or subtracting a constant. Right? So that means we only need to concern ourselves with the 275. Right? The formula, or the method we use, is the absolute value of the constant in the multiplier, which is negative 275, times the standard deviation of C in this case. So that basically is 275 times 0.36. And that gets us to 0.99. All right, so that means that the typical selling price for a chip from Chipcore will vary by about 99 cents from the mean of 21.70, about $1. And that's it. All right. So when you're doing these transformations, it's one thing you need to do is just identify that it is a linear transformation, right? We're taking this known information and we're adjusting it by some constants. In this case, we're adding and multiplying. We're subtracting and multiplying. And so that's a linear function, right? 25 minus 275c. Once you know that, then you just need to properly put those things in play with either the measure of center or measure of spread, or both. Is there anything I can clarify about this part? All right. So then, this will be available in the course. I'll have that posted at some point today. We're going to get started in our new chapter, chapter 7. All right. And that's going to be right here. So if you've got a notebook and you're taking notes, piece of paper, something to write with, now is the time. There's going to be essentially some new vocabulary today. This whole section is centered around essentially a lot of new vocab and how it relates to things we've seen already and how they're related to each other. It's a major part of section 7.1. All right. So here we are, 7.1. What is a sampling distribution? And chapter 7 is sampling distributions. So here we go. So in this section, we're going to be learning how to distinguish between a parameter and a statistic. Use the sampling distribution of a statistic to evaluate a claim about a parameter. Distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution of a statistic. Determine whether or not a statistic is an unbiased estimator of a population parameter. And describe the relationship between sample size and the variability of a statistic. All right. If this doesn't make sense yet, that's fine. That's why we're learning it today. So first, the process of statistical inference, which is essentially why we're starting this chapter. We're getting into more inference, involves using information from a sample to draw conclusions about a wider population, which is again something that we touched on in the very first chapter we did, chapter 4, about sampling, right? How to take a sample. Different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. So we start with the population, we take a sample, we collect the data from the representative sample, we make an inference about the population. This is the process we're involved in. Right? Ultimately, we want to say something about the entire population, right? Which we don't necessarily have time to sample the entire population, so we take that sample, collect data. Does anyone need a moment to write anything down from this screen? Please raise your hand. Parameters and statistics. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. A parameter is a number that describes some characteristic of the population. Right. Parameter, population, P. A statistic is a number that describes some characteristic of a sample. Statistic, sample. Right. So this is the way to help remember which one goes with which. Remember, S and P. Statistics come from samples and parameters come from populations. So you need to carefully read the context of problems now and decide, is this a sample, is this a population, am I dealing with a statistic, am I dealing with a parameter, right? These are the things we have to consider. We write the Greek letter mu for the population mean and X bar for the sample mean. You may have seen this X bar before in other courses, right? Represents the sample mean. We use P to represent a population proportion, right? In our previous examples, P has represented like probability of success, or it's the proportion for some outcome or some thing. Right? The sample proportion, P hat, is used to estimate the unknown parameter P. Okay, so if it's the proportion from a sample, it is simply an estimate for the unknown proportion of the population. And this is because it might be impossible to know the exact proportion within a population, because possibly the population is just too huge. You can't sample everyone. So you're using P hat, sample proportion. Okay, and this is just a little like, call it P hat. It's a circumflex. It's a little like up arrow thing. It's above the 6 on your keyboard. That guy. So you need a moment to write anything down from this slide. Raise your hand. So how can X bar be an accurate estimate of mu? After all, different random samples would produce different values of X bar. Right? And this is true. We can have variance from one sample to the next. That's typical. This basic fact is called sampling variability. The value of a statistic varies in repeated random sampling. To make sense of sampling variability, we ask, what would happen if we took many samples? In other words, we have a population, we sample, right? What does that all mean? How we can put this all together? Is there anything I can clarify so far? And does anyone need a moment to write anything down? And I'm sorry if you can hear the snoring in the background. That is my pug. He is sleeping and he snores loudly. If we took every one of the possible samples of size n from a population, calculated the sample proportion for each, and graphed all those values, we'd have a sampling distribution. And when they say proportion, right, we could be dealing with like a percentile. That could be a mean, median, right? There's lots of different measures we could be using for proportion. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the sample population. In practice, it's difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process of taking many samples. All right. We can use software to do simulations. The book might provide us with the simulation data. That's pretty common in this case. And we'll see an example of something that will simulate for us in our activity tomorrow. So it's, again, the main focus here is a sampling distribution of a statistic is the distribution of values taken by the statistic. And a statistic is, some measure, right? It could be the mean, median, quartile, percentile, something like that. It's a position, right? It's a measure of position. Do we need a moment to write anything down? There are actually 3 distinct distributions involved when we sample repeatedly and measure a variable of interest. There is the population distribution, and this gives the values of the variable for all the individuals in the population. The distribution of sample data shows the values of the variable for all individuals in the sample. And the sampling distribution shows the statistic values from all the possible samples of the same size from the population. All right. So population is everyone. Distribution of a sample is the actual results you got from that sample in a histogram or dot plot. The sampling distribution takes like possibly the mean of your sample distribution, like your distribution of the sample, and puts that as a single point in the sampling distribution over many samples. Right? You get many means of that sample data, and that creates the sampling distribution. Which is done in visual form. Yeah. So we start with our population. And this is referring to an example from the textbook about selecting chips, right? You have a blue or a red chip, like a poker chip. Probability of selecting one or the other is 50%. We do simple random sample. Our sample is of size 20. Right? In this sample, we get the following results. We get a probability of red being 0.4. And that is p hat because it's a sample probability, sample proportion. This random sample, again of size 20, yielded a different p hat, 0.55. This one again is another one, different p hat, 0.65. Each of these proportions then goes on to the dot plot here for the sampling distribution. So, and this obviously doesn't look like individual dots. But there's individual dots. They're just stacked on top of each other very closely. Each dot in this sampling distribution represents the p hat from one SRS of size 20, which was taken from the population. Okay, so that's how these 3 distributions are related and how they go. We can kind of go from one to the other. So we need a moment to write anything down or copy anything from this slide or the previous one with the definitions. Describing sampling and distributions. The fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider the center, spread, and shape. Center, biased and unbiased estimators. In the CHIPS example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips, p equaling 0.5? If we look at our sampling distribution of p hat, note that the center of the approximate sampling distribution is close to 0.5. We'd kind of expect based on this, the center should be right around 0.5. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 0.5. A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Right, so again, we want unbiased estimators, right? And we can tell it's unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. And can you please raise your hand if you need a moment to write anything down? Next is spread. Low variability is better. Right. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. Right, so we see two examples here. One where the sample size for each sample was 100. This is a sampling distribution for samples of size 1000. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. It's just less variability, meaning we'll be closer to the true value. Because this has more spread, it's more varied, right? There's a possibility it won't be as accurate and it won't be as close to the true value. So larger samples are better. Larger samples typically result in a lower variability. Is there anything I can clarify? Does anyone need a moment to write anything down? So there are general rules for describing how the spread of the sampling distribution of a statistic decreases as the sample size increases. One important and surprising fact is that the variability of a statistic in repeated sampling does not depend very much on the size of the population. All right. So the size of the population doesn't matter as much as the size of the sample. Having a larger sample is typically will result in a smaller variability. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined mainly by the size of the random sample. Larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population. As long as the population is at least 10 times larger than the sample, meaning that the 10% condition has been satisfied. All right, so the sample should be 10% or less than the population. So we can't go, really shouldn't go larger than 10% of the population. is essentially kind of what's it's saying. Otherwise, we're starting to play around with the population. Does anyone need a moment to write anything down from this slide? So then we get to bias, variability, and shape. We can think of the true value of the population parameter as the bullseye on a target, and of the sample statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. So we have these 4 different targets here. One is high bias, we're way off center, but low variability, very well clustered right here. We can have low bias and high variability, right? So these are all around the center, so it's probably going to average out to be close to the center, but it's super varied. We have high bias and high variability, right? Just off everywhere. And the ideal, which would be no bias and low variability, right? We're just right on the mark. Bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. Remember, we talked about different types of bias and things like that. Those are all things that can help. That it just means that we're either overestimating or underestimating what it should be. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results, right? Which is another problem, right? If it's just too varied, right, we're not really getting. It's possible that you're not getting very trustworthy results. There's just too much of a spread. Right? We like things to be close to the value we're looking at. Helps give us confidence in our results. You see, we need a moment to write anything down from this screen. All right, then that is the basis for section 7.1. Right? We know what a parameter and statistic is and that they are different. Parameters are for population, statistics are for samples. Right? We can use the sampling distribution of a statistic to evaluate a claim about a parameter. Right? And that is what we saw with the blue and red chip distribution. Right? We can see that sampling distribution yields the same value as the parameter in the population. We can distinguish among the distribution of a population, distribution of a sample, and sampling distribution. Those are 3 different things, though they are related. We can determine whether or not a statistic is an unbiased estimator of a population parameter. And we can describe the relationship between sample size and variability of a statistic. Larger sample, less variability. And with that, we reach the end of the lesson for 7.1. So tomorrow we will get practice with section 7.1 and those concepts and vocabulary and some ways to apply those things. Before we go further, real quick, here's a quick peek into what's available for Chapter 7 in Canvas. If we look at the modules, Chapter 6, right? If you've completed everything, you'll have check marks next to the 2 assessments. Otherwise, you'll have like a check mark to what's completed. And this little guy saying it's not done yet. Right? Chapter 7 is now open. Right? I had it restricted up until I think yesterday because we're now in Chapter 7 as a class, so now it's open. The notes and resources are ready to go. Right? The study guides are in each section. And the practice problem set is ready as well for each section. I do not have the solutions completed yet. Same with the assessments. I should be getting those built this week or next week so that they will be ready in time. All right. So we do have our resources available, kind of like Chapter 6. There's lots of things in here. We've got the study guide, presentation you just saw, AP Daily videos, videos of examples from the textbook, and I actually have the link to the textbook and the pages that correspond with section 7.1 here as well if you want to look through the textbook digitally or the one you have at home, whichever you want. All right, so we have all those things available. All right, so chapter 7 is basically ready to go in Canvas as well. So there's that.